All right, we'll do one last problem on this chapter 1 stuff. So I like this one. This is kind of a, again, getting you a little more to an actual type of design. Here's a structure that's loaded up in a certain way, and you have to check or size a couple of different elements here. All right. So here we have 2 bars, BA and BC. All right. They're pinned together. They're pinned at joint A, B, and C. Those are all pin joints. And you can see here is sort of the top view if you looked down at A. So this bolt going through A acts in single shear along that plane. All right? At B, the way B is, it kind of comes around this element here, AB, comes around and grabs. See, this is A, that's element AB, and this is supposed to be element BC. And here you can see this pin is in double shear. So it has 2 shear planes acting on it. Okay? The problem here wants you to size BC, okay, basically the thickness of BC out of the paper, because it sets the height at 1.5 inches. And also the 2 pins, all right? So I actually might break this video up into 2 parts so I can get it onto YouTube. And what it tells you is, as is typical, that the pins are made of a different material than the elements, so it gives you a allowable normal yield stress in element BC, and then also an allowable shear stress, average shear stress in the pins. All right. Now here there is no factor safety, so here they're calling it allowable. So that's basically what we got before. That would be maybe that if they're designing to yield, that's the yield over the factor safety, or if it's brittle and they're designing to actual failure or some other fatigue type of loading, like drop it down from failure, it's that value divided by the factor safety. But they've already done that for you, so what we're going to consider is those values are going to be the ones that we're going to design to, all right? All right, so we actually have 3 elements that we have to size here. The pin at A, the pin at B, and then also member BC. Okay? And I guess it's allowing you to say that. I think what it's inferring here is that the pins at A and B are the same diameter. You don't want to have different size pins to make your life easier. So what we have to do is figure out the max stress in both of these. One of them will be higher. That'll be our limiting design case, and that's what we'll use to design the diameter of the pin. Okay? All right. Let's first do member BC. Okay? That's the normal stress part. Okay? So this is in problem F. This is a review problem 103, and it's on page 62 in Hibbler. And I've written on top of the piece of paper that I don't like to write on, but okay, fine. I have to zoom out again. One of these days I'll get used to this and actually zoom out. All right, there we go. There's my page. Oops, too much. Zoom out a little bit more. There we go. All right, so this is the problem we're going to do. All right? Okay, so first let's consider element BC. All right? So it really doesn't matter what free body diagram I look at. Well, actually it probably does, because I guess one of them has more information than the other. But I need to know something about the reaction loads, whether I consider this one or this one. This is the one that's sort of at the top. This would be point C. This is point A. At point A, at both A and C, we allow for pin types of reaction forces. Okay? All right. Now, the other thing we use here to make our life simpler, okay, this is B. And this is a distributed force, all right? So in this situation, I really can't draw a section that'll let me get at the force in this element without really dealing with the reaction forces, okay? So we need to get the reaction forces. Well, if you look at this, you'll say, oh, well, I have 4 reaction forces, so this is statically indeterminate. But you have to remember, we didn't explicitly go over this in review, but since we're pinned both at B and C, this is a 2-force member, so that means you actually know the direction that this reaction force acts in. So the reaction force actually is not like this. You actually know the reaction force acts along the line BC. Okay? So it's it's pinned to both sides, and there's no other loads in the element. So the reaction forces have to be along the line BC. Okay? At A, that's not the case. Although it's pinned to both A and B, we have this intermediary distributed load, which might has to be compensated. And you can obviously see that from the free body diagram anyway. If we just act along AB, that'll give you this force, but you need a Y force to counteract this downward distributed load. Okay? All right. So in fact, what that does is once you recognize that it's a 2-point member, or 2-force member, that you know the angle, so you have the magnitude, that's the unknown, and then the x and y components at A. So I'm going to call this, let's call this reaction X, reaction Y at point A, and this is just going to be the reaction at C. All right, so we know the direction. All right. All right. Well, let's figure those out. The way to do that is actually we have to consider first the free body diagram on the whole entity. So let me do that on a piece of paper. Okay? So we need to figure out the reaction forces for the whole body. Let's see if they gave us enough information on that. Let's draw the free body diagram for the whole structure. Okay? So we have Rx at A, Ry at A, and we have Rc. And I know this angle here is 60. I should have drawn it up a little more to get my, my sines and cosines correct. Remember we took that last time, that actually it's usually kind of beneficial to kind of sketch. Well, let me do it. I should just do it. I should do what I say. So it helps kind of get the other elements correct, okay? It helps us get our angles when we do the cosine side. It keeps a good sanity check. All right, so Rx at A, Ry at A, and then here is Rc. C, I got the C up there. All right. This is 60. Okay, so if we do sum of forces in the x direction, and I guess the other thing we can do here is we can replace the distributed load with its equivalent point load. So that is going to be acting through the center, right? 4 feet, and this is 4 feet, right? And the magnitude of this is the 2 kip per foot times 8 feet, or in other words, 16 kips acting downward, okay? All right, so if we do sum of forces in the x, that gives me Rc. Its x component is cosine of 60, and then plus Rx at A, and that has to equal 0. Cosine of 60 is 1/2. And then right, so this just gives you the relationship that RC has to equal -2 times RAX component. All right, let's do sum of forces in the y direction. Those have to equal 0. So that gives me RC sine of 60, or that's rad 3 on 2. The P is acting downward, so that's minus 16 kips, and then RY acts up, and that has to equal 0. All right, finally, we have to do sum of moments. And unfortunately, how am I going to do this? I don't know where this point is. All right? So if I were to try to do sum of moments, well, I guess you could still figure it out. If you did sum of moments around A, you could figure out this moment arm. Okay? Or we could do sum of moments around B, and the nice thing about that is it takes out the moments from RC because it acts along that line. And these are a lot easier to deal with. So let's do that. Let's do sum of moments around point B. Those have to go to 0. All right, so P puts a negative moment. It's negative 60 kips, and its moment arm is 4. Let's put everything in inches. 4 times 12 inches. That's the moment of P around B. The X force does no moment, and has no moment arm around B, but the Y reaction force A gives me a positive moment. So that's positive RYA, and its moment arm is 8 feet, or 8 times 12 inches. And that has to equal 0. All right, so that'll immediately give me RY and A. So the 12s will cancel out. So I get RY at A has to equal 16 kips times 4 divided by 8. The 12s cancel out. And that gives me 8,000 pounds. Okay. Now that I know that, I can use that to solve for RC in this equation. So that'll give me, using this equation, putting this into here, and then that'll give me RC times rad 3 on 2 minus 16 kip plus 8 kip has to equal 0. Or in other words, RC is equal to 2 on rad 3. This is a minus 8 kips, bring to the right-hand side. That becomes a positive 8 kips, right? And that equals 16 divided by rad 3. Oh, wait a second. 16 into 3 radical. All right. So that's 9.24 kips. And then the last one we can do is get the reactions at in the x direction of A from this equation. So now I can take these values, put it into the sum of forces in the x direction, and that'll give me the following equation. R A at x equals minus 1/2 RC, but I know that that is 9.24 kips. So that gives me minus 4.5, 4.67 kips. Just to do them ahead of me. Okay, so actually, it's flipped the other way. All right. So actually, Rx is acting this way. So this element here will be in tension. All right. All right. So now that we got all the reaction forces, all right, we can go solve what's going on in element BC. And actually, I think I'll probably stop here and do that in another video. Okay.